Let's take a look at one of those test problems. This was a piecewise-defined function. It was cosecant of pi x over 6 if the absolute value between, or the absolute value of x minus 2 was less than or equal to 2. So that means the distance between 2 and x is less than or equal to 2. So in interval notation, that is 0 to 4. And the rest of the function was defined to be the horizontal line 2 if the absolute value of x and 2 is greater than 2. So this means we need to be further away from 2 than 2 units. So that would be negative infinity to 0 and then 4 to infinity. So there's a typo here that we'll fix right here. So this should say 4 here. Just a second. So really what we need to do is we need to find where the cosecant pi x over 6 is undefined, and then we need to find the connector points. And the connector points for where we change from cosecant to 2 would be at 0 and 4. So we just need to check at 0 and 4 and then where the cosecant pi x over 6 is undefined. So cosecant of pi x over 6 is the same thing as 1 over sine of pi x over 6. And what we need to do is we need to find out when is the sign 0, because when the sign is 0, then that'll be where we're undefined. So sine pi x over 6 is equal to 0 when pi x over 6 is equal to 0, pi, 2 pi, 3 pi, or in the negative direction also. So we'll just say k pi, so that'll cover all of them where k is going to be an integer. So if we solve that for x, we would multiply both sides by 6 and then divide by pi, so the pi's would cancel, and we would just have x is equal to 6k. So this is just a sequence, and x would be in this set negative 12, negative 6, 0, 6, 12, etc. And we really only need to consider which values in this set actually fall in the interval 0 to 4, because that's the only time that we're looking at cosecant pi x over 6. So the only one we really need to consider is 0, which happens to be one of the endpoints we were going to consider anyways. Since 0 is going to give us a sign of 0, which is 0, this is where it's going to be undefined. So we can say that f of x is discontinuous because it's undefined at x equals 0. So now all we really need to do is we need to check the other endpoint, which is 4. So what we can do is we can use limits to approach from both the left and the right hand side of 4. So if we look at from the left side of 4, that would be in the interval 0 to 4. So we look like the cosecant of pi x over 6. And we plug that in, and then if you want to crunch those numbers, it's approximately negative, or it was positive 1.5. Now, this is more or less, this could have been a pre-calculus problem. We can use limits to kind of talk about approaching 4 from the left and the right. Now, if we approach from the right-hand side, we're in the open interval 4 to infinity, so we look like the line y equals 2. And that's limit is 2. So what we have here is from the left and the right, those limits don't match up. So if those limits don't match up, then the function has some sort of, in this case it has a gap. So this is discontinuous at 4. And that's the only thing we needed to check. We needed to check, are we continuing, we only need to check where the cosecant was undefined in the interval 0 to 4, and the only place that happened was 0, and then we had to check the endpoints 0 and 4, and that was it. So we have two places where it's discontinuous at 0 and 4. If we look at the other example, we use cotangent pi x over 6, and the same setup in terms of the intervals. So one was 0 to 4, and the other one was negative infinity to 0, union 4 to infinity. Cotangent of pi x over 6 is cosine pi x over 6 divided by sine pi x over 6. Sine of pi x over 6 is equal to 0 when the sine pi x over 6, oops, I said we should say this instead here, but it's going to end up being the same argument. So sine of pi x over 6 is equal to 0 when pi x over 6 is equal to k pi. So after this, it's the same argument as the last one. Okay. The other test problem we had was the intermediate value theorem, which applies to f is continuous on a closed interval AB, f of a and f of b are not equal, and k is between f of a and f of b. So when we're talking about theorems in mathematics, there's no extra assumptions. We use the minimalistic amount of assumptions as possible. So you absolutely need continuity on a closed interval. You need the endpoints, outputs to be not equal, and then the k has to be in between f of a and f of b. If we don't have all three of those conditions met, then the theorem is not true. So on your test, well, let's go ahead and put in the conclusion. The conclusion is there exists a c in the closed interval AB such that f of c is equal to 0. On our test, we considered changing it from closed interval AB to open interval AB. And in class we showed a piecewise-defined function. I think this is slightly different, but f of a is going to be negative 2, f of b is going to be 2, and then we just have this piecewise-defined function. And then in the middle we have something at height negative 1, just a horizontal line at height negative 1 with open circles there. Now, it meets the condition that it's continuous on AB, on the open interval AB. However, f of a is negative 2, f of b is 2, and 0 is in between 2 and negative 2. However, do you see any of the graph, the pink graph, crossing the x-axis, and that doesn't happen. So we need it to be closed interval. Otherwise, we can have a situation where we're continuous on the open interval AB. However, the theorem does not hold. So every assumption is important.